Space and time were once thought to be entirely separate, two distinct dimensions that never touched. Then one idea changed everything, and we discovered they are woven together like threads in a single fabric, bending and stretching wherever matter exists. Tonight, in this sleep documentary, we explore the quiet mysteries of spacetime and let these sleepy science facts help you fall asleep fast as the universe gently unfolds around you. Tonight, we journey through the fabric that holds everything together in this documentary for sleep. From the curvature near massive stars to the stretching of moments at incredible speeds, spacetime is the invisible stage upon which all existence performs its slow, eternal dance. This is science for sleep, where cosmic truths become a lullaby to guide you toward deep sleep. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will drift through the quiet architecture of the universe, carrying you softly through dimensions you cannot see but are always part of. There is nothing to memorize, nothing to remember. Just listen and let your mind wander through the fabric of reality itself. Have you ever wondered what time truly is, or why it seems to flow only forward? You are not alone. If these soothing facts help you rest, consider subscribing to join our community of curious sleepers, one sleepy soul at a time. Now let your shoulders drop, let the weight of the day dissolve, and take one slow breath. Feel the stillness around you, and know that you are already drifting, already part of this vast, patient cosmos. Let us begin. Space and time are not separate, but a single four-dimensional fabric called spacetime. For centuries, humans understood space as the stage upon which events unfold, and time as the clock that measures their passing, two entirely different things that existed independently of one another. But the universe held a deeper truth waiting to be revealed. Space and time are not two separate entities, but one continuous fabric woven together, stretching and bending as a single structure. Imagine a vast sheet extending in every direction, not just the three dimensions you can move through, but also the dimension of time itself, all connected, all influencing one another. Every moment you experience, every step you take, happens at a specific point within this unified fabric. You are not merely moving through space while time passes around you. You are tracing a path through spacetime itself. It is a quiet truth that changes everything. Albert Einstein first proposed the concept of spacetime in his 1905 special theory of relativity. In the early 20th century, a young patent clerk in Switzerland began asking questions that would unravel the foundations of physics. Albert Einstein imagined what it would be like to ride alongside a beam of light, and from that thought experiment emerged one of the most revolutionary ideas in history. His special theory of relativity revealed that space and time are not fixed and absolute but flexible, relative to the observer's motion. What appears as 1 meter to you might appear shorter to someone moving past at tremendous speed. What feels like 1 second might stretch or shrink for another observer. Einstein wove these findings into a single framework, showing that space and time are fundamentally linked, each affecting the other depending on how you move. From a quiet office in Bern, one mind reshaped our understanding of the cosmos. In spacetime, every event has 4 coordinates, 3 for space and 1 for time. When you describe where something happens, you naturally think in 3 dimensions, perhaps telling someone to meet you at a street corner on the 5th floor. But in the language of spacetime, that description is incomplete without one more piece, when every event in the universe, from the flicker of a distant star to the beat of your heart, exists at a unique point defined by 4 coordinates, 3 for location in space and 1 for its moment in time. These 4 numbers pinpoint exactly where and when something occurs within the fabric of reality. Without the time coordinate, an event is merely a place with no context. Without the spatial coordinates, it is merely a moment with no location. Together, they form the complete address of every occurrence. You exist right now at your own unique four-dimensional point, an address that will never be repeated. The speed of light is the cosmic speed limit, never changing regardless of how fast you travel. There is one constant in the universe that refuses to bend, and that is the speed of light. At roughly 300,000 kilometers per second, light travels faster than anything else, and nothing with mass can ever reach or exceed this absolute limit. If you were traveling at half the speed of light and shone a torch forward, you might expect the light to move faster, but it does not. It still travels at exactly the speed of light. The universe compensates by warping time and space around you, stretching moments and shrinking distances so that light always maintains its constant pace. This speed limit is not merely a rule about motion, it is woven into the very structure of space-time, a boundary that keeps the universe coherent and prevents cause from ever arriving before effect. It is the universe's unbreakable promise. Time slows down for objects moving at extremely high speeds, a phenomenon called time dilation. As you move faster through space, something peculiar happens to time. It begins to slow down for you, stretching like honey dripping from a spoon, each moment lasting longer than it would for someone standing still. This phenomenon is not a trick of perception, but a fundamental feature of how spacetime operates. The faster you travel, the slower your clock ticks compared to stationary clocks. If you could approach the speed of light, time would slow to a crawl, and what feels like minutes for you could be years for those you left behind. This effect has been confirmed with precise atomic clocks aboard fast-moving aircraft and satellites. It is not science fiction, but measured reality. The universe trades one kind of motion for another, as if traveling quickly through space means traveling slowly through time. Speed buys you more moments. And from the stretching of moments at great speeds, we turn to something even more profound, the way mass itself reshapes the fabric of reality. Mass causes spacetime to curve, and this curvature is what we experience as gravity. Einstein's greatest insight came 10 years after his special theory, when he realized that gravity is not a force pulling objects together, but the result of spacetime being curved by mass. Imagine placing a heavy ball on a stretched rubber sheet. The sheet bends around the ball, and smaller objects nearby roll toward it, not because they are pulled, but because they follow the curved surface. This is essentially what happens throughout the universe in 4 dimensions. Every object with mass, from planets to the atoms in your body, creates a curve in spacetime around it. Other objects simply follow these curves, traveling along the straightest path through bent geometry. What you feel as gravity holding you to Earth is your body following the curvature created by our planet's mass. Gravity is geometry, and the universe bends itself around everything within it. The more massive an object, the deeper the curve it creates in the fabric of spacetime. Not all curves in spacetime are equal in depth or in consequence. A grain of sand barely dimples the fabric at all, its effect unmeasurably tiny. But a planet like Earth creates a noticeable well deep enough to hold an atmosphere and keep the moon in orbit. The sun curves spacetime far more dramatically, keeping 8 planets and countless smaller bodies circling for billions of years. Neutron stars and black holes create curves steep enough to trap light itself. The relationship is straightforward. More mass means deeper curvature, and deeper curvature means stronger gravity. This is why you weigh less on the moon than on Earth. Its smaller mass creates a shallower curve. The universe is a landscape of varying depths, hills and valleys in the fabric of reality, with the most massive objects sitting at the bottom of the deepest wells. Everything rolls toward what is heavy. Objects in free fall are not being pulled by a force, but simply following the curves of spacetime. When you drop a stone and watch it fall, It appears as though some invisible hand is pulling it downward. But in Einstein's view, nothing is pulling at all. The stone is moving through space-time along the most natural path available, and that path leads toward Earth because the planet's mass has curved the geometry in that direction. An astronaut floating in the International Space Station is not experiencing zero gravity. They are in constant free fall around the planet, following a curved path that keeps them perpetually falling without ever hitting the ground. This is why free fall feels like weightlessness. You are moving exactly as space-time dictates, with no other forces interfering. The sensation of weight you feel standing comes not from gravity pulling down, but from the floor pushing up, preventing you from following your natural curved path. Falling is freedom. Light bends when passing near massive objects because it follows the curvature of space-time. Light always travels in straight lines. This was long considered a fundamental truth, but Einstein revealed that what looks straight depends on the shape of space you move through. When light passes near a massive object like a star, the curvature of space-time bends its path, causing it to curve around the mass rather than continuing straight. This phenomenon, called gravitational lensing, allows astronomers to see galaxies hidden behind other galaxies, their light bent around the obstruction. Sometimes a single distant galaxy appears as multiple images arranged in a ring around a closer massive object. The universe magnifies itself, using space-time curvature as a cosmic lens. Even the light reaching your eyes from distant stars has followed a curved path through all the space-time dimples created by matter between here and there. Nothing travels truly straight. This bending of light was first confirmed during a solar eclipse in 1919. Einstein's general theory predicted that starlight passing close to the sun would be bent by the curvature of space-time. But testing this required seeing stars near the sun, possible only during a total solar eclipse when the moon blocks the sun's light. In 1919, 2 expeditions set out to observe an eclipse, one to the island of Principe off Africa and another to Brazil. When the moon's shadow fell and stars near the sun became visible, astronomers photographed their positions and compared them to where those stars normally appeared. The results matched Einstein's predictions. The starlight had bent around the sun. This confirmation made headlines worldwide and transformed Einstein into a global celebrity overnight. A simple observation during minutes of darkness proved that space-time curves around every massive object. The universe had revealed one of its deepest secrets. Clocks tick slower in stronger gravitational fields, a fact proven by precise atomic measurements. Gravity does not merely pull objects together, it also reaches into time itself and slows it down. The stronger the gravitational field, the slower time passes. A clock at the top of a mountain ticks ever so slightly faster than a clock at sea level, because the mountain clock sits farther from Earth's center, where gravity is weaker. This effect is incredibly small in everyday life, measured in billionths of a second, but it is real and has been confirmed with atomic clocks of extraordinary precision. If you lived your entire life on the ground floor rather than the top floor, you would age slightly less than someone above, though the difference would be too tiny to notice. Near massive objects like neutron stars, this time difference becomes dramatic. Minutes on the surface might equal hours far away. Gravity bends not just space, but time. And as we consider time flowing differently in different places, let us explore the most extreme benders of space-time, the black holes. Black holes create such deep curves in space-time that nothing, not even light, can escape. When a massive star dies and collapses under its own gravity, it can compress into a point so small and dense that it punches a hole through the fabric of space-time. This is a black hole, an object whose gravitational curve is so steep that anything crossing too close falls inward forever. Not even light, the fastest thing in the universe, can climb back out of that well. From outside, a black hole appears as a sphere of perfect darkness, revealing itself only by the way it bends light from stars behind it or pulls in surrounding matter. It is a place where spacetime has been stretched beyond all limits, where the familiar rules of the cosmos begin to fail. Black holes are scattered throughout the universe, ancient remnants of dead stars and colossal monsters lurking at the hearts of galaxies. They are the universe's darkest sculptures, hidden yet ever present. At the edge of a black hole lies the event horizon, the point of no return. The event horizon is not a physical surface you could touch, but an invisible boundary in spacetime, the point beyond which nothing can ever return. Cross this threshold and you are committed. No force in the universe can pull you back out. Light emitted from inside the horizon cannot reach outside observers, which is why black holes appear black. The size of this boundary depends on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would be only a few kilometers across, while supermassive black holes at galactic centers have horizons spanning millions of kilometers. From far away, you might watch a friend approach a black hole and see them slow down as they near the horizon, their image fading and reddening, but they would never quite seem to cross it. Time itself appears to freeze at that boundary when viewed from outside. Time near a black hole slows so dramatically that an observer far away would see someone falling in freeze at the horizon. The gravitational time dilation near a black hole reaches extreme proportions. If you watch someone fall toward the event horizon from a safe distance, you would see their descent slow to a crawl as they approached. Their movements would become sluggish, their watch would appear to tick slower and slower, and their image would redden as light struggled to escape the deepening gravity well. From your perspective, they would never actually cross the horizon, frozen forever at its edge in an eternal moment. But from the falling person's perspective, they would feel nothing unusual at the crossing. Time for them would continue normally as they sailed past the point of no return. This is one of the strangest paradoxes of spacetime, two observers experiencing radically different versions of the same event. Near a black hole, there is no single agreed-upon present. Inside a black hole, the roles of space and time may actually swap. Once you cross the event horizon, the mathematics of general relativity suggests something deeply strange happens to the nature of space and time. Inside the black hole, the direction toward the singularity at the center becomes like a direction in time, inevitable and inescapable. Just as you cannot avoid moving forward in time in our everyday world, inside a black hole, you cannot avoid moving inward toward the singularity. It is not merely that you lack the speed to escape. The very geometry of spacetime is arranged so that all paths, all futures lead to the center. The spatial directions you knew outside become more like moments in time, places you can remember but never return to. This swapping of roles is one of the most mind-bending predictions of Einstein's equations, a place where our intuitions about space and time simply cease to apply. Inside a black hole, falling is not a choice but a certainty. And as these thoughts of warped time settle around you, there is no need to hold onto any of them. Let them drift through your mind like starlight through the cosmos. Take a slow breath if you wish, and let your body sink a little deeper into stillness. The center of a black hole is called a singularity, where space-time curvature becomes infinite. At the heart of every black hole lies a singularity, a point where all the mass has been crushed into an infinitely small space. Here, space-time curvature becomes infinite, and the equations of general relativity break down entirely, producing nonsensical answers. Density becomes infinite, volume becomes zero. our understanding of physics cannot describe what happens at this point. Some physicists believe the singularity is a sign that our theories are incomplete, that a new understanding combining gravity with quantum mechanics is needed to explain what truly happens at a black hole's core. Perhaps the singularity is not truly a point, but something more complex hidden by our ignorance. For now, it remains one of the deepest mysteries in physics, a place where space-time is torn beyond recognition. The singularity is where the universe keeps its most guarded secrets. Rotating black holes drag space-time around them in a phenomenon called frame dragging. Most black holes in the universe are not still but spinning, often rotating at tremendous speeds. When a massive object spins, it does not simply sit within space-time but drags the fabric around with it, twisting space and time into a kind of whirlpool. This effect is called frame dragging, and near a rotating black hole it becomes extreme. Anything near such a black hole, even light itself, gets caught up in this swirl and is forced to rotate along with the spinning space-time. There is a region called the ergosphere surrounding a rotating black hole where nothing can remain stationary, where the dragging is so powerful that standing still becomes physically impossible. You would be swept along with the rotation of space itself. This twisting of space-time is not science fiction. It is a measured and confirmed prediction of Einstein's equations. Rotation reshapes reality. Even Earth, with its modest mass, causes a tiny amount of frame dragging measured by satellites. Frame dragging is not limited to the extreme environments near black holes. Any rotating mass drags space-time around with it, including our own planet. Earth's rotation creates an incredibly tiny twisting of the fabric around it, so small that it was only confirmed in 2011 by a NASA satellite called Gravity Probe B. The satellite carried gyroscopes of extraordinary precision, and over the course of its mission, it measured how Earth's rotation caused a slight precession, a gentle wobbling, in the gyroscope's orientation. The effect was exactly what Einstein's equations predicted, confirming that even our familiar world participates in the deep strangeness of space-time. Right now, as you lie here, the Earth beneath you is ever so slightly dragging space and time along with its daily spin. You are caught in a slow cosmic whirlpool without ever noticing. And from the spinning fabric near black holes, we shift to the ripples that travel through space-time itself. When massive objects accelerate, they create ripples in space-time called gravitational waves. Just as a stone dropped into still water creates spreading ripples, accelerating masses create ripples in space-time itself. These gravitational waves travel outward at the speed of light, stretching and squeezing space as they pass. When two black holes spiral toward each other and merge, they shake space-time so violently that the ripples can be detected billions of light years away. When neutron stars collide, they too send waves racing through the cosmos. These ripples are incredibly faint by the time they reach us, stretching space by less than the width of an atom. Yet they carry information about the most violent events in the universe, messages written in the very fabric of reality. Every moment, gravitational waves from countless cosmic events are passing through your body, though you will never feel them. The universe hums with invisible tremors. Gravitational waves travel at the speed of light, stretching and squeezing space as they pass. As a gravitational wave passes through you, space is stretched in one direction and compressed in the perpendicular direction. Then the pattern reverses, over and over as the wave oscillates by. If you could see the effect, you would notice objects around you becoming slightly taller and thinner, then shorter and wider as the wave moved through. In reality, the stretching caused by waves from distant events is far too small to notice with human senses, often changing distances by less than the diameter of an atom. But these waves travel at exactly the speed of light, carrying energy and information about their violent origins across the cosmos. They move through everything, through planets, through stars, through you, without stopping or slowing. Gravitational waves are whispers from the most energetic events, rippling silently through the quiet darkness of space. The first direct detection of gravitational waves occurred in 2015, confirming Einstein's century-old prediction. For 100 years after Einstein predicted them, gravitational waves remained beyond our ability to detect. They were simply too faint, their stretching of space too tiny to measure with any instrument humanity possessed. Then, in September 2015, two detectors on opposite sides of the United States simultaneously felt the same brief shiver, a tiny ripple lasting less than a second. Analysis revealed it was the signature of two black holes, each about 30 times the mass of our Sun, spiraling together and merging over 1 billion light-years away. The announcement came months later and electrified the scientific world. A completely new window on the universe had opened, one that did not rely on light but on the vibrations of spacetime itself. What was once a theoretical prediction had become measured reality, and the cosmos suddenly had a new voice. When two black holes merge, they release more energy in gravitational waves than all the stars in the observable universe combined. The collision of two black holes is the most violent event known to occur in the universe. In the final moments before they merge, the two objects spiral around each other at nearly the speed of light, releasing tremendous amounts of energy in the form of gravitational waves. For a brief instant, this energy output exceeds the combined light of every star in the observable universe. Yet none of this energy comes as light or heat. It is pure vibration of spacetime itself, invisible to any telescope. The merged black hole settles down into a larger, quieter remnant, ringing like a struck bell as it radiates away its final distortions. These cosmic collisions happen somewhere in the universe roughly once every few minutes, sending ripples through the fabric of reality that eventually wash past Earth. The universe is filled with these silent catastrophes. Gravitational wave detectors can measure changes in distance smaller than 1/10,000th the width of a proton. Detecting gravitational waves requires measuring changes in distance so small they seem impossible. The detectors use laser beams bounced between mirrors set 4 kilometers apart, watching for tiny variations in the time it takes light to travel that distance. When a gravitational wave passes, it stretches space in one direction while compressing it in another, causing the tiniest difference in the laser paths. The change in distance is less than 1/10,000th the width of a single proton, a measurement so precise it pushes the limits of what physics allows. To achieve this sensitivity, engineers had to isolate the mirrors from every imaginable vibration, from passing trucks to ocean waves to the thermal jiggling of atoms themselves. The result is an instrument capable of hearing the faintest whispers of the cosmos. It is a triumph of human ingenuity. Neutron star collisions produce gravitational waves that carry information about the densest matter in existence. Neutron stars are the collapsed cores of dead massive stars, objects containing more mass than our Sun squeezed into a sphere, only about 20 kilometers across. The matter inside is so dense that a teaspoon would weigh billions of tons. When two neutron stars spiral together and collide, they release gravitational waves that carry unique information about this extreme matter. Unlike black hole mergers, neutron star collisions also produce light and radiation, allowing astronomers to observe the same event in multiple ways. The first such observation occurred in 2017, when gravitational waves and light arrived together from a collision 130 million light-years away. These events also forge heavy elements like gold and platinum. The jewelry you wear may contain atoms created in such a cosmic collision. And from these cosmic tremors, we turn to the paradoxes that emerge when we consider time more deeply. The twin paradox describes how one twin traveling at high speed would age slower than the twin who stays on Earth. Imagine two twins, one stays on Earth while the other boards a spacecraft and travels to a distant star at nearly the speed of light, then returns. When they reunite, the traveling twin has aged less than the one who stayed home. This is not a trick of perception, but a real physical difference. The twin who moved at high speed experienced time more slowly, their clock ticking fewer seconds during the journey than the clock of their sibling on Earth. If the journey took 10 years as measured on Earth, the traveling twin might have aged only a few years. The asymmetry arises because the traveling twin accelerated and changed direction, experiences that the Earth twin did not share. This thought experiment reveals that time is personal, not universal. Your path through spacetime determines how much time you experience. This effect has been measured with atomic clocks flown on aeroplanes, confirming that motion through space affects the passage of time. In 1971, physicists placed extremely precise atomic clocks aboard commercial airplanes and flew them around the world, once eastward and once westward. When the clocks returned, they were compared to identical clocks that had remained on the ground. The differences were exactly what Einstein's equations predicted. The eastward flying clock, moving with Earth's rotation, lost a tiny fraction of a second. The westward clock gained time. These differences were only billionths of a second, but they matched theory to remarkable precision. What had been a thought experiment became measured fact. Time really does pass differently depending on how you move through space. This effect applies to everything that moves, including you. Every time you travel, you age slightly less than if you had stayed still. Motion buys you time. Astronauts on the International Space Station age slightly slower than people on Earth due to their speed. The International Space Station orbits Earth at about 28,000 kilometers per hour, completing a full circle around the planet roughly every 90 minutes. At this speed, time dilation becomes measurable. Astronauts living aboard the station experience time slightly slower than people on the ground. For every 6 months spent in orbit, an astronaut ages about 7 milliseconds less than their colleagues on Earth. It is not much, a tiny fraction of a heartbeat, but it accumulates over longer missions. After a year in space, the difference approaches 15 milliseconds. This effect has been confirmed by comparing atomic clocks in orbit with those on the surface. The astronauts are literally traveling into a slightly different future than the rest of humanity. Speed steals small slices of time from every moment. At the same time, being farther from Earth's gravity makes astronauts' time run slightly faster. While speed slows time down, weaker gravity speeds it up. The International Space Station orbits about 400 kilometers above Earth's surface, where the gravitational pull is slightly weaker than at sea level. This means astronauts experience a tiny acceleration of time due to their altitude, partially offsetting the slowdown caused by their speed. On the station, this gravitational effect is smaller than the speed effect, so the net result is still a slowing of time. But the two influences work in opposite directions, creating a kind of temporal tug-of-war. For satellites in higher orbits, where speeds are lower and gravity is weaker, the gravitational effect can dominate, making their clocks run faster than those on Earth. Altitude and velocity together determine how time flows for any object in space. Every orbit is a balance of temporal forces. These two effects partially cancel each other, but speed wins, so astronauts return slightly younger than they would be otherwise. For astronauts on the International Space Station, the slowing of time due to speed is slightly larger than the speeding up due to weaker gravity. The net effect is that astronauts age a tiny bit less than they would have if they had stayed on Earth. After a typical 6-month mission, an astronaut returns about 7 milliseconds younger than they would otherwise be. Over the course of a career with multiple long missions, this difference can add up to fractions of a second. The record holder, a cosmonaut who spent over 2 years in orbit across multiple flights, is estimated to have aged about a 50th of a second less than the rest of humanity. It is not enough to notice, but it is absolutely real. Space travel is literally a form of time travel, carrying you into your own future ever so slightly faster. GPS satellites must account for both special and general relativistic effects, or positions would drift by kilometers each day. The Global Positioning System relies on precise timing to calculate your location. Satellites orbiting about 20,000 kilometers above Earth broadcast the exact time according to their onboard atomic clocks, and receivers on the ground use tiny differences in arrival times to triangulate position. But satellite clocks experience time differently than clocks on Earth. Their speed makes time run slower, while their altitude and weaker gravity makes time run faster. The net effect is that satellite clocks gain about 38 microseconds per day compared to ground clocks. Without corrections for these relativistic effects, GPS positions would drift by roughly 10 kilometers per day, making the system useless. Every time you use GPS to find your way, you rely on Einstein's theories. Relativity is not abstract physics, it is in your pocket. And as we consider time bending in our everyday technology, let us drift deeper into the fabric of the universe's earliest moments. Spacetime itself began with the Big Bang, approximately 13.8 billion years ago. The universe as we know it has a birthday, a moment when spacetime itself came into existence. About 13.8 billion years ago, everything that now fills the cosmos was compressed into an unimaginably tiny, hot, and dense state. Then, in an instant, the universe began to expand, and with that expansion came the very fabric of space and time. The Big Bang was not an explosion in space, it was the beginning of space, the sudden appearance of the stage upon which all existence would unfold. Every atom in your body, every star in the sky, every galaxy scattered across the void traces its origin back to that singular moment. Time itself only has meaning from that point onward, because before the Big Bang there was no before. The cosmos carried its own clock into existence, and that clock has been ticking ever since. Before the Big Bang, there was no space to move through and no time to measure. The question of what came before the Big Bang is one of the most profound puzzles in all of cosmology. In our everyday experience, every event has something that happened before it, a cause that precedes an effect. But the Big Bang marks the beginning of time itself, not just the beginning of matter and energy. If time only started with the Big Bang, then asking what happened before is like asking what is north of the North Pole. The question may simply have no meaning at all. Some theories suggest the universe emerged from a quantum fluctuation, a bubble of spacetime appearing from nothing. Others propose that our Big Bang was just one of many, with new universes constantly budding off from some greater multiverse. For now, we cannot see or measure anything from before that first moment. The Big Bang is the ultimate edge of all we can ever know. In the first fraction of a second, the universe underwent a period of rapid expansion called cosmic inflation. In the tiniest fraction of a second after the Big Bang, the universe went through an extraordinary growth spurt called cosmic inflation. During this brief period, spacetime expanded at a staggering rate, doubling in size over and over again in less time than it takes light to cross an atom. a region smaller than a proton inflated to become larger than the observable universe today, all in roughly a trillionth of a trillionth of a trillionth of a second. This rapid expansion smoothed out any irregularities in the early universe and explains why the cosmos looks so uniform in every direction we observe. It also stretched tiny quantum fluctuations into the seeds of galaxies, the slight density variations that would later grow under gravity. Inflation set the initial conditions for everything that followed. The universe was born in a rush of impossible growth. During inflation, spacetime expanded faster than the speed of light, which does not violate physics because space itself was stretching. The speed of light is the ultimate speed limit for objects moving through space, but inflation shows there is a loophole. During cosmic inflation, it was not objects moving through space that exceeded light speed, it was space itself that was stretching. Nothing within space was traveling faster than light, but the fabric of space was growing so rapidly that distant points were carried apart faster than light could ever travel between them. This is perfectly allowed by the laws of physics. The speed limit applies to motion through space, not to the expansion of space itself. Today, the universe continues to expand, and galaxies far enough away are receding from us faster than light for the same reason. They are not moving through space at superluminal speeds. Space is simply carrying them away. Expansion creates distance without motion. The cosmic microwave background radiation is a snapshot of spacetime when the universe was only 380,000 years old. Everywhere you look in the sky, there is a faint glow of microwave radiation, the oldest light in the universe. This cosmic microwave background was released about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. Before that, the cosmos was a hot fog of charged particles that scattered light constantly. When atoms formed, the fog cleared, and light from that era has been traveling through space ever since, stretched by the expansion of the universe into microwaves. By studying tiny variations in this ancient light, scientists have learned about the early structure of spacetime, the seeds of galaxies, and the age and composition of the universe. It is a photograph of the infant cosmos, taken billions of years before Earth existed. The universe is still expanding, and the rate of that expansion is accelerating due to dark energy. The expansion that began with the Big Bang has never stopped. Galaxies throughout the universe are moving apart from each other as the fabric of spacetime continues to stretch. But in 1998, astronomers discovered something unexpected. The expansion is not slowing down as gravity would suggest. It is actually speeding up. Something is pushing the universe apart faster and faster, and we call this mysterious influence dark energy. Its nature remains one of the greatest unsolved puzzles in physics. We cannot see it, we cannot detect it directly, but its effects are unmistakable. The universe is not just coasting after the Big Bang, it is accelerating into an ever faster expansion. In the distant future, this acceleration may carry galaxies so far apart that distant civilizations would see nothing but emptiness. Dark energy is quietly reshaping the fate of everything. Dark energy makes up about 68% of the universe and drives spacetime to stretch faster over time. When scientists add up all the matter we can see, all the atoms in stars and planets and gas clouds, it accounts for only about 5% of the universe's total content. Dark matter, an invisible substance that only interacts through gravity, makes up another 27%. The remaining 68% is dark energy, a mysterious component that permeates all of space and drives its accelerating expansion. Unlike matter, which slows expansion through gravitational attraction, dark energy has a repulsive effect, pushing space apart. As the universe expands, dark energy does not dilute, it maintains its density, so its influence grows over time. Eventually, dark energy will dominate completely, stretching spacetime so fast that even nearby galaxies will fade from view. We live in an era when we can still see the distant universe. That window may not last. The observable universe has a radius of about 46 billion light-years, even though it is only 13.8 billion years old. It seems like a paradox. The universe is about 13.8 billion years old, so you might expect the farthest objects we can see to be about 13.8 billion light-years away. But the observable universe stretches roughly 46 billion light-years in every direction. The explanation lies in the expansion of space. Light from the most distant objects began its journey toward us billions of years ago, but while that light was traveling, space itself was expanding, carrying those objects farther away. By the time the light reaches us, the source has moved much farther than the light's travel time would suggest. The edge of the observable universe is not a physical barrier, but simply the limit beyond which light has not had time to reach us since the Big Bang. The true universe may extend far beyond what we can ever observe. Galaxies at the edge of the observable universe are receding faster than light due to the expansion of spacetime between us. The most distant galaxies we can observe are moving away from us at speeds that exceed light, carried by the expansion of spacetime. This does not violate the laws of physics because these galaxies are not moving through space faster than light. Rather, the space between us and them is stretching so rapidly that the total recession speed surpasses light's pace. Light emitted by these galaxies today will never reach us because new space is being created faster than light can cross it. We can only see them because light they emitted long ago, when they were closer, has been traveling toward us ever since. As the universe continues to accelerate, more and more galaxies will cross this horizon and fade from view. Eventually, the distant universe will be forever hidden from any observer in our cosmic neighborhood. The visible cosmos is slowly shrinking. The shape of spacetime on cosmic scales appears to be flat, meaning parallel lines remain parallel forever. When cosmologists talk about the shape of the universe, they do not mean its edges but its geometry. On the largest scales, spacetime appears to be flat, which means parallel lines remain parallel no matter how far they extend. In a positively curved universe, like the surface of a sphere, parallel lines would eventually meet. In a negatively curved universe, like a saddle, they would diverge forever. But careful measurements of the cosmic microwave background suggest our universe is flat to remarkable precision. This flatness is closely tied to the total energy density of the cosmos and confirms predictions from the theory of inflation. A flat universe can expand forever without ever collapsing back on itself. The geometry we measure today tells us the cosmos will likely continue stretching into an endless future. Spacetime has no edges, only eternal expansion. And as these vast distances and ancient times settle softly around you, let your breathing slow. In this sleepy science journey, there is no hurry. Let the immensity of spacetime cradle you gently, like a slow wave carrying you toward rest. If the universe had slightly more matter, spacetime would curve back on itself like the surface of a sphere. Imagine the entire cosmos curving gently inward like the surface of a ball. In a positively curved universe, parallel lines would eventually meet, just as lines of longitude on a globe converge at the poles. This kind of universe would be finite yet without edges, a vast space you could travel through forever and eventually return to where you started. Measurements of the cosmic microwave background suggest our universe is remarkably close to flat, but even a tiny positive curvature would have profound implications for its fate. A closed universe would eventually stop expanding and collapse back on itself in a big crunch, the reverse of the Big Bang. Everything that exists would be drawn back together into an unimaginably dense point. The shape of space determines the ultimate fate of all matter and energy within. If it had slightly less matter, space-time would curve like a saddle, open and ever-expanding. A negatively curved universe would stretch outward like a saddle, its geometry allowing parallel lines to diverge forever. In this open cosmos, space would expand without limit, carrying galaxies farther and farther apart until the universe became cold, dark, and impossibly lonely. The shape of space-time in such a universe would mean that no matter how far you traveled, you could never return to your starting point by moving in a straight line. Current observations suggest the universe is balanced on a knife edge between these extremes, appearing almost perfectly flat. This critical balance is extraordinarily precise, and even a slight deviation in the early universe would have led to wildly different outcomes. Whether we live in a universe destined to expand forever or eventually reverse remains one of the deepest questions in cosmology. And from the grand geometry of the cosmos, we descend to explore some of the strangest possibilities within spacetime. Wormholes are theoretical tunnels through spacetime that could connect distant points in the universe. Wormholes are shortcuts through the fabric of spacetime, theoretical passages that could link locations separated by billions of light years or even different moments in time. Picture folding a piece of paper so that two distant points touch, then punching a hole through both. Instead of traveling across the surface, you slip through the tunnel and arrive almost instantly. The mathematics of general relativity permits such structures to exist, though we have never observed one and do not know if nature allows them to form. If wormholes exist, they could revolutionize our understanding of space travel and the very nature of the cosmos. They might connect different regions of our universe or even link separate universes altogether. For now, wormholes remain tantalizing possibilities written in the language of equations. Einstein and physicist Nathan Rosen first described wormholes mathematically in 1935. In 1935, Albert Einstein and Nathan Rosen published a paper exploring solutions to the equations of general relativity that described bridges connecting separate regions of spacetime. These Einstein-Rosen bridges, as they came to be known, were the first mathematical description of what we now call wormholes. The pair was not looking for shortcuts through space, but rather investigating the nature of fundamental particles. Their work showed that the equations allowed for structures where 2 points in spacetime could be joined by a narrow throat. Though Einstein himself doubted such objects could actually exist or be traversed, his mathematics opened the door to decades of speculation and research. The term wormhole was coined later by physicist John Wheeler, evoking the image of a worm burrowing through an apple to create a shortcut. For a wormhole to remain open, it would require exotic matter with negative energy density. Keeping a wormhole open long enough to travel through would require something truly strange, a form of matter with negative energy density. Ordinary matter and energy curve spacetime in predictable ways, pulling things together through gravity. But to prop open a wormhole and prevent it from collapsing, you would need matter that pushes spacetime apart, matter that has less than zero energy. Such exotic matter has never been observed in any laboratory, though quantum physics hints that negative energy states might exist under very special circumstances. The Casimir effect, where two closely spaced metal plates experience a tiny attractive force, demonstrates that vacuum energy can behave in unexpected ways. Whether enough exotic matter could ever be gathered to stabilize a wormhole remains one of the great unknowns. For now, traversable wormholes remain in the realm of theory. No wormhole has ever been observed, but the mathematics of general relativity allows for their existence. Despite decades of searching, no one has ever found evidence that wormholes exist in our universe. No telescope has spotted the telltale gravitational signature. No particle accelerator has produced a fleeting tunnel through space. Yet the equations of general relativity, our best description of gravity and spacetime, contain solutions that describe these bridges between distant points. Mathematics alone cannot tell us what nature actually permits, only what is logically consistent within a given framework. It is possible that some unknown principle of physics prevents wormholes from forming, or that they exist but are far too small or unstable to detect. The search continues because finding even indirect evidence of wormholes would transform our understanding of the cosmos. Until then, they remain beautiful theoretical possibilities waiting for experimental confirmation. Some physicists speculate that if wormholes exist, they could theoretically allow travel backward in time. If wormholes connect different points in space, could they also connect different moments in time? Some physicists have proposed that a wormhole with one mouth moving at high speed relative to the other could create a time difference between its two ends. You might enter one side in the year 2000 and exit the other decades earlier, effectively traveling backward into the past. Such a time machine would raise profound questions about causality and the nature of reality itself. Could you change events that have already happened? Would the universe somehow prevent such paradoxes from occurring through some natural law? These speculations push the boundaries of physics and philosophy alike. Whether time travel is truly possible or forever forbidden remains one of the deepest mysteries waiting to be discovered. The grandfather paradox questions what would happen if you traveled back and prevented your own birth. The grandfather paradox is a famous thought experiment that illustrates the strange implications of backward time travel. Imagine you travel into the past and prevent your grandparents from ever meeting. If they never meet, your parents are never born and neither are you. But if you were never born, how could you have traveled back in time to interfere in the first place? This logical contradiction has puzzled philosophers and physicists for generations. Some argue that such paradoxes prove time travel to the past is impossible, that the universe simply forbids events that would create contradictions. Others propose that physical laws might conspire to prevent paradoxical situations, ensuring consistency through some unknown mechanism. The grandfather paradox reveals just how strange our intuitions about time become when we consider altering the past. One proposed solution is the many worlds interpretation, where changing the past creates a new branching timeline. One way to escape the grandfather paradox is to suppose that changing the past does not alter your own history, but instead creates a new branch of reality. In the many worlds interpretation of quantum mechanics, every possible outcome of every event actually occurs, each in its own separate universe. If you traveled back and prevented your grandparents from meeting, you would simply create a new timeline where they never did, while your original timeline remains unchanged. You would exist in a universe where you were never born, but the you who made the journey still came from somewhere. This branching model avoids logical contradictions by allowing multiple histories to coexist. Whether such parallel timelines actually exist or are merely a clever philosophical escape remains an open question in physics. Closed time-like curves are paths through space-time that loop back to their starting point in time. In the mathematics of general relativity, certain solutions describe paths through spacetime that loop back on themselves, returning a traveler to their own past. These closed time-like curves would allow an object to travel through time and arrive at the same moment and place from which it departed. Such curves appear in theoretical models of rotating black holes and in certain wormhole configurations. If closed time-like curves exist, they would blur the distinction between past and future, raising profound questions about causality and free will. Many physicists believe that nature must contain some protection mechanism that prevents these loops from forming, though no one has yet identified what that mechanism might be. Closed time-like curves remain among the most fascinating and troubling possibilities allowed by our equations. And from these mind-bending possibilities, let us return to phenomena we can actually observe. Time flows at different rates at different altitudes, a fact measurable even between floors of a building. Time does not pass at the same rate everywhere, and this difference becomes measurable even in everyday settings. The closer you are to a massive object, the slower time ticks compared to someone farther away. On Earth, this means that time runs ever so slightly slower at sea level than on a mountaintop, and even between the ground floor and the top of a tall building, there is a tiny but real difference. These effects are incredibly small in our daily lives, far too subtle for human senses to detect, but modern atomic clocks are precise enough to measure them. Experiments have confirmed that clocks at higher altitudes gain a few billionths of a second over their counterparts below. The fabric of spacetime is not uniform, and gravity shapes the flow of time in ways that Einstein predicted over a century ago. Even in the ordinary world, time bends to the pull of mass. The most precise atomic clocks can detect the time difference caused by raising them just 1 centimeter. The precision of modern atomic clocks is truly staggering. These devices keep time by counting the vibrations of atoms, typically cesium or strontium, which oscillate at extraordinarily stable frequencies. The best optical lattice clocks are so accurate that they would neither gain nor lose a second over the entire age of the universe. With such precision, scientists can detect the gravitational time dilation caused by raising a clock just 1 centimeter higher. At that tiny difference in altitude, the clock ticks faster by an almost incomprehensibly small amount, yet the measurement is clear and repeatable. These experiments confirm that Einstein's predictions hold true even at the smallest scales we can test. Our understanding of spacetime has been verified by instruments of almost magical sensitivity, revealing that time itself is woven into the geometry of the cosmos. Muons, particles created in the upper atmosphere, should decay before reaching Earth, but time dilation allows many to survive the journey. Muons are subatomic particles created when cosmic rays from deep space collide with atoms high in Earth's atmosphere. These particles are unstable, decaying with a half-life of just over 2 millionths of a second. At that rate, even traveling near the speed of light, muons should decay long before reaching the surface. Yet detectors on the ground register a surprisingly large number of muons arriving from above. The explanation lies in time dilation. From our perspective, the muons are moving so fast that their internal clocks appear to run slow, stretching their brief lifetimes long enough to reach us. From the muons' perspective, it is the distance to Earth that contracts, shortening their journey. Either way, the result is the same. Relativity allows these fleeting particles to survive a trip that classical physics would forbid. Particles in accelerators experience time so slowly that their lifetimes can extend thousands of times longer than at rest. In particle accelerators, beams of subatomic particles are pushed to speeds approaching the speed of light. At these extreme velocities, time dilation becomes dramatic. Particles that would normally decay in a fraction of a microsecond can instead travel around the accelerator ring for what seems like an eternity from our perspective. their internal clocks have slowed so much that their lifetimes stretch by factors of thousands or even millions. This effect is not theoretical. It is measured routinely in laboratories around the world and is essential for the operation of experiments at facilities like CERN. Without time dilation, many of the particles physicists wish to study would vanish before they could be observed. Relativity transforms the fleeting into the lasting, giving scientists precious extra moments to probe the fundamental nature of matter and energy. The faster you move through space, the slower you move through time, and vice versa. There is a profound trade-off between motion through space and motion through time. Everything in the universe is always moving through space-time at the same combined rate, the speed of light. When you stand still relative to another observer, all of your motion is through time, and you age at the maximum possible rate. But when you begin moving through space, some of that motion is diverted away from time, and you age more slowly. The faster you travel through space, the slower you travel through time. At everyday speeds, this effect is negligible, but as you approach the speed of light, it becomes truly dramatic. This is not a trick of perception or measurement error, but a fundamental feature of the geometry of the universe. Time and space are intertwined, and how you move through one directly affects how you move through the other. At the speed of light, time would stop entirely, but no object with mass can ever reach that speed. If you could somehow travel at the speed of light, time would come to a complete standstill. From your perspective, no time would pass at all, no matter how far you traveled. But this is a speed reserved only for massless particles like photons. Any object with mass requires more and more energy to accelerate as it approaches light speed, and the energy needed becomes infinite before you can ever reach it. This cosmic speed limit ensures that no spaceship, no matter how powerful, can ever truly attain that forbidden velocity. The universe enforces this rule through the very structure of spacetime. As you push closer and closer to light speed, your mass effectively increases, resisting further acceleration. The speed of light remains forever out of reach for anything with substance, a boundary woven into the fabric of reality. Photons, which travel at light speed, experience no passage of time at all from their own perspective. Photons are the particles of light, and they travel at the ultimate speed limit of the universe. Because they have no mass, they are born moving at light speed and can never slow down. From the perspective of a photon, time does not pass at all. There is no before and after, no sequence of moments, only a single eternal instant. A photon emitted from a distant star and absorbed by your eye billions of years later experiences that entire journey as happening all at once, with no duration whatsoever in between. This is a strange and almost incomprehensible state of existence, but it is precisely what the mathematics of relativity tells us. Photons inhabit a world without time, carrying energy and information across the cosmos while experiencing nothing of the journey themselves. Light lives in a timeless and eternal now. For a photon, its entire journey across billions of light years happens in a single instant. Consider a photon that leaves a distant galaxy and travels across the universe for billions of years before reaching your eye. From your perspective, that photon has been on an epic journey, crossing unimaginable distances over cosmic timescales. But from the photon's perspective, if we can even speak of such a thing, the journey takes no time at all. The moment of emission and the moment of absorption are the same instant, separated by no experience of duration. This is one of the strangest consequences of traveling at light speed. The photon connects 2 points in spacetime that are separated by billions of light years, yet for the photon itself, those points are simultaneous. It is as if the photon exists outside of time, touching distant moments of cosmic history in a single timeless flash. Light sees the universe in a way we can barely imagine. And as we consider the timeless existence of light, let us explore how space itself can change. An object moving at high speed contracts in the direction of motion, a phenomenon called length contraction. Just as time slows for objects moving at high speeds, space itself contracts in the direction of motion. An object traveling near the speed of light would appear squashed along its direction of travel to an outside observer. This is not an optical illusion, but a real physical effect, a consequence of the way spacetime transforms between different frames of reference. The faster you go, the more compressed you become in the eyes of those you pass. At everyday speeds, this contraction is far too small to notice, but as you approach light speed, it becomes dramatic. A meter stick moving at 99% of light speed would appear only about 14 centimeters long to a stationary observer. Length contraction is the spatial counterpart to time dilation, and together they reveal how deeply space and time are intertwined. A spacecraft traveling at 90% of light speed would appear squashed to an outside observer. Imagine a spacecraft hurtling through space at 90% of the speed of light. To an observer watching from a planet, the ship would appear dramatically flattened in the direction it is traveling. The nose and tail would seem pressed together, as if the spacecraft had been squeezed by an invisible force. Yet from inside the ship, the crew would notice nothing unusual. Their vessel would look perfectly normal, its dimensions unchanged. It is the universe outside that would appear transformed, with stars and planets seeming compressed along the direction of travel. This symmetry is a hallmark of relativity. Each observer sees the other's lengths contracted, and both perspectives are equally valid. Space and time adjust themselves to preserve the laws of physics, reshaping our intuitions about shape and distance in the process. From inside the spacecraft, everything would look normal, but the universe outside would appear compressed. For the crew inside a spacecraft traveling at tremendous speed, the interior of their vessel looks entirely normal. Their clocks tick at the usual rate, their bodies feel no different, and distances within the ship remain unchanged. But when they look out the window at the universe rushing past, something strange appears. Stars and galaxies seem squashed in the direction of travel, as if the cosmos itself has been compressed. The distance to their destination appears shorter than it would to someone watching from home. This length contraction of the external universe is the flip side of time dilation and makes interstellar travel at least theoretically possible within a human lifetime. A journey to a star 10 light-years away might take only a few years from the traveler's perspective. The universe shrinks to accommodate those who dare to move fast enough through it. Simultaneity is relative, meaning two events that appear simultaneous to one observer may not be to another. In our everyday experience, it seems obvious that two events either happen at the same time or they do not. But relativity reveals that simultaneity is not absolute. Two events that appear simultaneous to one observer may occur at different times for another observer moving at a different speed. Imagine two lightning bolts striking the front and back of a moving train at the same instant, according to someone standing on the platform. A passenger on the train, moving toward one bolt and away from the other, would see them strike at different times. Neither observer is wrong. They simply have different but equally valid perspectives on when things happen. This relativity of simultaneity is one of the most counterintuitive consequences of Einstein's theory. It shows that time is not a universal constant, but depends on how you move through spacetime. This relativity of simultaneity is not an illusion, but a fundamental feature of how spacetime works. It might be tempting to dismiss the relativity of simultaneity as some kind of measurement error or perceptual trick, but it is neither. The disagreement about when events occur is built into the very structure of spacetime itself. There is no hidden truth about which events are really simultaneous. The concept itself depends on your frame of reference. This has profound implications for our understanding of time. If two distant events cannot be agreed upon as simultaneous by all observers, then the idea of a universal now becomes meaningless. Different observers literally inhabit different slices of space-time, experiencing different present moments. The relativity of simultaneity is not a flaw in our measurements, but a deep feature of reality, one that forces us to rethink our most basic assumptions about time and existence. The block universe theory suggests that past, present, and future all exist equally and eternally. The block universe is a way of thinking about spacetime in which all of time exists at once. Past, present, and future are not separate realities, but different locations in a four-dimensional structure that simply is. Just as all points in space exist simultaneously, so too do all moments in time. From this perspective, the Battle of Hastings, your breakfast this morning, and events 1,000 years in the future are all equally real, all part of the same eternal block of spacetime. Nothing truly comes into being or passes away. Everything just exists at its own coordinates in the block. This view arises naturally from the equations of relativity, which treat time and space on equal footing. The block universe challenges our deepest intuitions about change and becoming, suggesting that the flow of time may be an illusion. In this view, time does not flow, and the feeling of the present moment is just a feature of consciousness. If the block universe picture is correct, then time does not flow from past to future. Nothing moves through time because there is no outside perspective from which such movement could be observed. The sensation that time is passing, that the present moment is special and different from other moments, may be a product of how our minds work rather than a feature of external reality. Our brains create memories and anticipations, giving us the feeling that we are moving through time, but this may be an elaborate construction. From the perspective of the block, every version of you across your entire life exists simultaneously, each experiencing its own present moment. This is a deeply strange idea, and not all physicists accept it, but it shows how radically our understanding of time has shifted since Einstein first reimagined space and time as one unified fabric. And as these profound ideas about time settle around you, there is nothing you need to solve or understand right now. Let the mysteries rest beside you like old companions. Breathe slowly and let your thoughts drift like leaves on still water. The arrow of time describes why we experience time moving forward but never backward. We remember the past but not the future. We can influence what happens tomorrow but not what happened yesterday. Eggs break but never unbreak, and people grow old but never young. This one-way flow of time is so familiar that we rarely question it, yet the fundamental laws of physics are almost entirely symmetric with respect to time. If you filmed a ball bouncing and played the footage backward, the physics would still make perfect sense. So why does time seem to flow in only one direction? This puzzle is known as the arrow of time, and despite centuries of deep thought, it remains one of the deepest and most profound mysteries in all of physics. The answer may lie in the very origins of the universe, in the special conditions that prevailed at the Big Bang and set the entire cosmos on its one-way journey from order toward entropy and disorder. Most laws of physics work equally well forward and backward in time, making the arrow of time a deep puzzle. If you watch a video of planets orbiting a star, you cannot tell whether it is being played forward or backward. The same is true for particles bouncing off each other, waves propagating through space, or light traveling between galaxies. The equations that describe these processes work equally well in both directions of time. This fundamental time symmetry is built into almost every law of physics we have discovered. Yet our everyday experience is filled with irreversible processes, broken glass that never reassembles, heat that never spontaneously flows from cold to hot. The contrast between the time-symmetric laws and the time-asymmetric experience of daily life is one of the great puzzles of physics. Something beyond the basic equations of motion must explain why time feels like it moves in only one direction. The second law of thermodynamics, which states that entropy always increases, may explain why time has a direction. Entropy is a measure of disorder, or more precisely, the number of microscopic arrangements that correspond to a given macroscopic state. The second law of thermodynamics tells us that in any isolated system, entropy tends to increase over time. A deck of cards, once shuffled, is unlikely to return to order by further shuffling. An ice cube in warm water will melt, spreading its coldness until everything reaches the same temperature. This relentless march toward higher entropy gives time its arrow. The future is the direction in which things become more disordered, more random, more mixed. The second law is not fundamental in the same sense as conservation of energy. It is a statistical truth about the overwhelming likelihood of moving toward higher entropy states, but it may be the key to understanding why time feels like it flows. The past is the direction in which entropy was lower, and the future is where it grows. If entropy increases toward the future, then by definition it must have been lower in the past. This simple observation has profound implications. The arrow of time points from states of lower entropy to states of higher entropy, and the past is simply the direction in which the universe was more ordered. At the Big Bang, the cosmos was in an extraordinarily low entropy state, and everything that has happened since has been a gradual unwinding toward higher disorder. The formation of galaxies, the evolution of life, and the thoughts you are having right now are all part of this cosmic slide toward greater entropy. The past feels different from the future because it was different. It was a time when the universe contained more usable energy and structure. Time's arrow is carved not in the laws of physics, but in the initial conditions of our cosmos. Memory exists because brains record information about the lower entropy past. Why do we remember yesterday but not tomorrow? The answer lies in entropy. Memories are physical records stored in our brains, and creating a record requires energy and organization. When you form a memory, your brain moves from a higher entropy state to a lower entropy state locally. But this is only possible because the environment absorbs the excess entropy, keeping the total entropy of the universe increasing. The act of recording information about the past is thermodynamically linked to the arrow of time. We remember the past because it is the direction of lower entropy, the direction from which organized information can flow into our present. If the universe were running backward, with entropy decreasing, our memories would point the other way. Memory is not a passive recording, but an active process embedded in the thermodynamic structure of the cosmos. And from the nature of time's arrow, we turn to the smallest scales where spacetime itself may behave strangely. At the Planck scale, about 10 to the minus 35 meters, spacetime may become grainy rather than smooth. Zoom in far enough on any surface and you will eventually see atoms and the space between them. What happens if you zoom in on space itself? At everyday scales, spacetime appears perfectly smooth and continuous, but at the Planck scale, roughly 10 to the minus 35 meters, this smoothness may break down. At such incomprehensibly tiny distances, smaller than any particle we have ever observed, spacetime might become foamy, grainy, or quantized into discrete chunks. The Planck length is so small that if an atom were scaled up to the size of the observable universe, the Planck length would still be smaller than a grain of sand. We have no instruments capable of probing such scales, but theoretical physics suggests that the familiar fabric of spacetime may give way to something far stranger at its most fundamental level. Quantum mechanics and general relativity do not yet fit together into a single unified theory. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity explains gravity and the curvature of spacetime at cosmic distances. Both theories have been tested to extraordinary precision and have never been found wrong within their domains. Yet when physicists try to combine them, the mathematics breaks down. Attempts to apply quantum rules to gravity produce infinite answers that make no physical sense. This incompatibility is one of the greatest unsolved problems in physics. A theory of quantum gravity would unify our understanding of the very large and the very small, revealing how spacetime behaves at its most fundamental level. Many approaches have been proposed, but none has yet been confirmed by experiment. The search for quantum gravity remains one of the great quests of modern science. Loop quantum gravity suggests that spacetime is made of tiny discrete loops rather than being continuous. Loop quantum gravity is one of the leading candidates for a theory that unifies quantum mechanics and gravity. In this framework, spacetime is not a smooth background, but is woven from tiny loops of gravitational field, much like fabric is woven from individual threads. Space comes in discrete chunks, the smallest possible volumes, and time advances in tiny steps rather than flowing continuously. According to this theory, there is a minimum length and a minimum time, below which the concepts of space and time simply do not apply. The loops connect and interact, forming a network called a spin foam that evolves over time. Loop quantum gravity makes specific predictions about what might have happened at the Big Bang and inside black holes, though these predictions remain extremely difficult to test with current technology. String theory proposes that spacetime has 10 or 11 dimensions, most of which are curled up too small to detect. String theory is another approach to unifying physics, proposing that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings of energy. The way a string vibrates determines what kind of particle it appears to be, much as the vibration of a guitar string determines its musical note. For the mathematics of string theory to work, spacetime must have more than 4 dimensions, typically 10 or 11. The extra dimensions are not hidden because they are invisible, but because they are curled up so tightly that we simply cannot detect them. Imagine a garden hose. From far away it looks like a one-dimensional line, but up close you see it has a circular cross-section. The extra dimensions of string theory may be curled up at the Planck scale, forever beyond our direct reach. The holographic principle suggests that all the information in a region of space may be encoded on its boundary. A hologram is a 2-dimensional surface that encodes a 3-dimensional image. The holographic principle suggests that something similar may be true of the universe itself. All the information about what happens in a volume of space might be fully encoded on the boundary surrounding that volume, like a cosmic hologram. This idea arose from the study of black holes, whose entropy turns out to depend on their surface area rather than their volume. If the holographic principle is correct, then the 3-dimensional world we experience may be a projection from information stored on a distant 2-dimensional surface. This does not mean our world is an illusion, but rather that there may be an alternative description of reality in fewer dimensions. The holographic principle hints at deep connections between gravity, information, and the nature of spacetime. Some physicists believe spacetime itself may emerge from something more fundamental, like quantum entanglement. For over a century, physicists have treated spacetime as the stage on which physics happens. but a growing number of researchers suspect that spacetime is not fundamental at all. Instead, it may emerge from something deeper, perhaps from the web of quantum entanglement that connects particles across the universe. Entanglement is the strange quantum phenomenon in which two particles remain correlated no matter how far apart they are. Recent theoretical work suggests that the geometry of spacetime, the distances and angles we measure, may be encoded in the pattern of entanglement among quantum systems. If this is true, then space and time are not the ultimate building blocks of reality, but rather arise from quantum relationships. The very fabric of the cosmos may be woven from invisible threads of correlation. The ER equals EPR conjecture links wormholes to quantum entanglement between particles. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a startling idea that wormholes and quantum entanglement might be two descriptions of the same underlying phenomenon. The conjecture is called ER equals EPR, after the Einstein-Rosen paper on wormholes and the Einstein-Podolsky-Rosen paper on entanglement. According to this proposal, every pair of entangled particles is connected by a tiny wormhole, a minuscule bridge through spacetime. The wormhole is far too small to send any information through, but it represents a deep connection between the particles. If true, this conjecture would unite two of the strangest features of physics, showing that the quantum correlations between particles and the geometry of spacetime are intimately related. It is a speculative but profound idea that may reshape our understanding of reality. Black hole thermodynamics suggests that black holes have temperature and entropy related to their surface area. In the early 1970s, physicist Jacob Bekenstein proposed that black holes have entropy, a measure of hidden information, proportional to the area of their event horizons. Shortly after, Stephen Hawking showed that black holes also have temperature and emit faint radiation as a result. These discoveries connected black holes to the laws of thermodynamics, revealing that the darkest objects in the universe obey the same rules as hot gases and steam engines. The entropy of a black hole is enormous, suggesting that an unimaginable amount of information is encoded on its surface. This connection between gravity, quantum mechanics, and thermodynamics has become a cornerstone of theoretical physics, hinting at deep truths about the nature of spacetime, information, and the fundamental structure of reality. Hawking radiation allows black holes to slowly evaporate over unimaginably long timescales. Nothing can escape from within a black hole, but the region just outside the event horizon is not quite empty. Quantum fluctuations constantly produce pairs of particles that briefly exist before annihilating each other. Near a black hole, one particle of a pair can fall in while the other escapes, carrying energy away from the black hole. Over time, this process, known as Hawking radiation, causes the black hole to lose mass and gradually shrink. The radiation is incredibly faint for stellar mass black holes, far weaker than the cosmic microwave background radiation. A black hole the mass of the Sun would take longer than the current age of the universe multiplied by itself many times over to evaporate completely. But in principle, all black holes will eventually and inevitably fade away, leaving behind only the radiation they emitted. The information paradox asks whether information that falls into a black hole is truly lost forever. When something falls into a black hole, it seems to be gone forever, destroyed by the singularity at the center. But quantum mechanics insists that information can never be truly destroyed, only scrambled and rearranged. If a black hole eventually evaporates through Hawking radiation, what happens to all the information about the matter that fell in? Is it lost forever, or does it somehow escape encoded in the radiation? This puzzle, known as the information paradox, has troubled physicists for decades. Various solutions have been proposed, from firewalls at the event horizon to subtle correlations in the Hawking radiation. The resolution may require a complete theory of quantum gravity. Whatever the answer proves to be, it will reveal deep truths about the relationship between information, gravity, and the fabric of spacetime. And as we consider the mysteries at the edges of our understanding, let us reflect on what spacetime means for existence itself. Every atom in your body exists at a specific point in spacetime, connected to everything else through the same fabric. You are here, right now, occupying a particular location in space and a particular moment in time. Every atom that makes up your body sits at its own coordinates in the four-dimensional fabric of spacetime. The carbon in your bones, forged in ancient stars, has traced a path through the cosmos that spans billions of years. The oxygen you breathe was once part of distant nebulae. You are not separate from the universe, but embedded deeply within it, woven into the same fabric that holds galaxies in place and guides light across the void. The spacetime that curves around black holes is the same spacetime that cradles you now. There is no boundary where you end and the cosmos begins. You exist as a particular pattern in the universal tapestry, connected to everything else by the threads of space and time. The light reaching your eyes from distant stars has traveled through spacetime for millions of years to reach you. When you look up at the stars, the light entering your eyes has been traveling for an astonishingly long time. Even the light from our closest stellar neighbor, Proxima Centauri, has been on its journey for more than 4 years. The bright stars of Orion are hundreds of light years away, meaning the photons you see left those stars during the Renaissance or even before. Light from the Andromeda Galaxy has been traveling for over 2 million years, setting out long before humans had even evolved. Every glance at the night sky is an act of time travel, your eyes receiving messages from the distant past. The universe communicates with us through ancient light, and we piece together its story from these cosmic letters. You are a witness to history written across the heavens, reading the past in the present moment. When you look at the night sky, you are looking back in time, seeing stars as they were long ago. Because light takes time to travel, every single observation of the universe is an observation of the past. You do not see the sun as it is now, but as it was roughly 8 minutes ago. The moon appears to you as it was about 1 1/3 seconds ago. Stars in the night sky show themselves as they were years, decades, or centuries in the past. Galaxies seen through telescopes reveal conditions that existed millions or even billions of years ago. There is no way to see the universe as it is right now because information itself takes time to reach us. In a very real sense, the night sky is a time machine, showing us not a single moment, but a tapestry of many different eras layered together. The deeper we look into space, the further back in time we see, until we reach the cosmic microwave background, the oldest light of all. Gravity, the force that keeps you grounded, is simply your body following the curves of spacetime. The weight you feel pressing you into your bed is not a force pulling you down, but the result of curved spacetime. The Earth's mass warps the fabric of spacetime around it, and your body follows the most natural path through that curved geometry. If there were no floor beneath you, you would continue along that path, falling freely toward the center of the Earth. But the bed pushes back against you, preventing that motion and creating the sensation of weight. From the perspective of general relativity, gravity is not a force at all but the geometry of spacetime itself. You are constantly trying to follow a straight line through curved space, and the resistance you feel is the universe reminding you of its shape. Gravity is the curvature of spacetime made tangible, a gentle hand guiding everything along the contours of the cosmos. Rest now in its quiet embrace. The bed beneath you creates a tiny dimple in space-time, and you rest within that gentle curve. Every single object with mass, no matter how small, creates its own curvature in space-time. Your bed, your pillow, even your own body all dimple the fabric of reality in their own tiny ways. These curves are far too slight for any instrument to measure, but they are there, rippling outward in principle to the farthest reaches of the cosmos. You rest not on a flat surface, but in a gentle valley of space-time created by everything all around you. The Earth's much larger curve dominates, but every atom adds its tiny contribution. You are nestled in a landscape of invisible geometry, held by the subtle warping of space and time. The universe cradles you in curves too gentle to feel, but ever present. Sleep comes so easily when you realize you are supported by the very fabric of existence itself, bending softly beneath and around you. Your heartbeat sends ripples through your body, and in an impossibly tiny way, through space-time itself. With every beat of your heart, a small amount of mass shifts position within your chest. This movement, like any acceleration of matter, generates gravitational waves, tiny ripples in the fabric of space-time. The waves your heartbeat produces are so unimaginably faint that no instrument could ever hope to detect them, but they are real. In principle, they spread outward at the speed of light, carrying a whisper of your existence into the cosmos. You are a source of gravitational radiation, a beacon pulsing gently into the universe with each heartbeat. The same physics that governs colliding black holes governs the rhythms of your body, just on a vastly smaller scale. You are connected to the cosmos through every breath and every beat, a living participant in the dance of space-time, sending silent signals into the infinite dark. The gravitational influence of your body extends, in principle, to the farthest reaches of the universe. Gravity has no edge, no boundary beyond which it ceases to act. The gravitational field of your body, though incredibly weak, extends outward forever, diminishing with distance but never reaching zero. In principle, the atoms of distant galaxies feel a vanishingly small tug from your presence. You are gravitationally connected to every particle in the observable universe. Of course, this influence is so tiny as to be utterly meaningless in practical terms, swamped by countless stronger effects. But the principle remains. There is no isolation in the cosmos. Everything pulls on everything else, bound together by the infinite reach of gravity. You are not a solitary island, but part of a web of attraction that spans the entirety of space and time. The universe knows you are here, in the gentlest possible way, reaching back toward you as you reach toward it. Time passes slightly faster for your head than for your feet because your head is farther from Earth's center. As you lie in bed, time ticks at different rates for different parts of your body. Your head, being slightly farther from the center of the Earth, experiences a weaker gravitational field and therefore ages ever so slightly faster than your feet. Over the course of a lifetime, this difference adds up to a few billionths of a second. It is far too small to notice or to have any effect on your life, but it is real. The same gravitational time dilation that causes clocks on satellites to run differently from clocks on the ground applies to you. You are a living demonstration of general relativity, with every part of your body existing in a slightly different flow of time. The universe treats your head and your feet as occupying different temporal landscapes, separated by mere centimeters, but distinct in their experience of time. This difference is far too small to notice, but measurable with the most sensitive instruments. The fact that time runs differently at different altitudes is not a theoretical abstraction, but a measured reality. The most precise atomic clocks in the world can detect the difference in time's passage caused by changes in height of just centimeters. Experiments have placed clocks on mountaintops and in valleys, on aeroplanes and on the ground, confirming again and again that gravity slows time. These measurements are essential for the operation of GPS satellites, which must account for both gravitational and velocity-based time dilation to provide accurate positioning. The technology you use daily depends on Einstein's insights about spacetime. What once seemed like a strange prediction of abstract physics has become an everyday engineering consideration, quietly built into the infrastructure of modern life and the devices in your pocket. The present moment you experience is already the past by the time your brain processes it. The moment you perceive as now is not truly now. Light from the world around you takes a tiny fraction of a second to reach your eyes, and your brain requires additional time to process that information into conscious experience. By the time you become aware of a sight, a sound, or a touch, the event that caused it has already receded into the past. You live in a perpetual state of slight delay, always experiencing reality, a heartbeat behind the actual moment. This lag is too brief to notice in daily life, but it reveals something profound about the nature of perception. You never experience the present directly, you only ever reconstruct it from the recent past. The now you feel is a memory already forming, a story your brain tells about what just happened. The true present is always a step ahead, forever just beyond your reach. And as you rest with these gentle truths about your place in spacetime, know that you are exactly where you need to be. These facts to fall asleep to ask nothing of you. Simply breathe and let the fabric of the universe hold you softly through the night. Consciousness may be the universe's way of experiencing its own spacetime from within. There is a strange and beautiful idea that awareness itself is a cosmic phenomenon. The matter that forms your brain was forged in ancient stars and scattered through the vastness of space over billions of years. Now, arranged just so, it has become capable of contemplating its own origins and meaning. You are spacetime looking back at itself, asking deep questions about its own nature. The atoms that think and wonder and dream were once adrift in the cold void, and they will return to the cosmos when your body is gone. But for this brief moment, they have assembled into a pattern that experiences. Perhaps consciousness is not an accident, but an inevitable expression of a universe complex enough to reflect upon itself. You are not merely in the cosmos, you are the cosmos made aware, a local fold in spacetime that has learned to wonder. Some philosophers suggest that the flow of time is an illusion created by how our brains process memories. The sense that time flows from past to future may be a trick of perception rather than a fundamental feature of reality. Our brains are constantly creating memories, and we interpret this process as movement through time. But in the equations of physics, there is no privileged direction. The laws work just as well running forwards as backwards. Some thinkers propose that all moments exist equally, and our consciousness simply moves its spotlight of attention along the timeline. Others argue that the feeling of flow is genuine, but emerges from deeper processes we do not yet fully understand. Either way, the experience of time passing is intimately tied to memory and cognition. As you rest quietly tonight, let go of the need to chase the future or cling to the past. Simply be here now, in this eternal present moment. The Alcubierre drive is a theoretical concept for bending spacetime to travel faster than light without violating physics. In 1994, physicist Miguel Alcubierre proposed a remarkable idea. Rather than accelerating a spacecraft to near light speed, which would require impossible amounts of energy, one might instead warp the fabric of spacetime itself. The ship would sit in a bubble of flat space, while space behind it expands and space ahead contracts. The bubble would surf along at any speed, even exceeding that of light, because nothing within it is actually moving through space. The spacecraft simply rides the wave. Of course, such a drive would require exotic matter with negative energy density, something we have never observed. but the concept demonstrates that our understanding of space-time allows for possibilities we can barely imagine. Dream tonight of voyages across the cosmos, carried gently by the bending of reality. Such a drive would contract space-time in front of a ship and expand it behind, carrying the ship along in a bubble. The warp bubble envisioned by Alcubierre is a beautiful piece of theoretical physics. Space-time ahead of the bubble compresses, bringing distant destinations closer, while space-time behind expands, pushing the point of origin farther away. The ship inside experiences no acceleration, no time dilation relative to its own reference frame, and no violation of the universal speed limit, because it is not moving through space, but rather space is moving around it. This mechanism sidesteps the usual problems with faster-than-light travel, though it creates new ones. The energy requirements may be unattainable, and the bubble might trap deadly radiation at its edge, yet the mathematics is sound. The universe seems to permit such structures in principle. Tonight, let your imagination glide through space-time on a warp bubble, free from the usual constraints. Time crystals are a new state of matter that repeats in time rather than in space, challenging our understanding of temporal symmetry. Ordinary crystals have atoms arranged in patterns that repeat through space, like wallpaper extending in 3 dimensions. Time crystals are different. They are systems that repeat their structure through time, oscillating in a regular pattern even in their lowest energy state. This seems to defy the usual expectation that systems at rest should be static. First proposed theoretically, and then created in laboratories around the world, time crystals represent a new phase of matter that pushes our understanding of what is possible. They hint that time and space may be even more deeply intertwined than we previously thought. As you lie peacefully still tonight, consider that even at rest, the universe can be dancing through time in patterns we are only beginning to discover and understand. And as we near the end of our journey through space-time, let us consider the grandest questions still waiting to be answered. S103, the chronology protection conjecture, suggests the laws of physics may prevent paradoxes by forbidding backwards time travel. Stephen Hawking proposed that the universe itself conspires to prevent time travel paradoxes. Every attempt to build a time machine might be thwarted by quantum effects or other physical processes. Closed time-like curves, the mathematical structures that would allow travel to the past, may always be unstable or require conditions that cannot be achieved. This conjecture protects history from interference, ensuring that cause always precedes effect. We do not know for certain whether chronology protection is a fundamental law, but the universe seems remarkably consistent about enforcing the arrow of time. Perhaps this is a profound feature of reality, a safeguard woven into the fabric of spacetime itself. Rest easy knowing that the past is safely behind you, unalterable and complete, while the future waits patiently ahead. The ultimate fate of spacetime remains unknown, with possibilities ranging from eternal expansion to eventual collapse. We do not yet know how the story of spacetime truly ends. The universe might expand forever, growing colder and emptier until even the last stars burn out. It might eventually reverse and collapse back into a singularity in a big crunch. Dark energy could tear apart galaxies, stars, and even atoms in a big rip, or something entirely unexpected could occur. The equations of cosmology offer several different possibilities, but observations have not yet revealed which fate awaits. For now, the universe continues its expansion, carrying us along in its flow. The end, whatever it may be, lies incomprehensibly far in the future. Tonight, there is no need to worry about such distant matters. Spacetime will hold steady for countless eons yet. Close your eyes and rest peacefully in the vastness of cosmic time. If dark energy continues to accelerate expansion, distant galaxies will eventually fade beyond our observable horizon. The accelerating expansion of the universe means that galaxies beyond a certain distance are receding from us faster than light can travel. In the distant future, this cosmic horizon will shrink. Galaxies we can see today will gradually redshift into invisibility as their light becomes too stretched to detect. Eventually, only our local group of galaxies will remain accessible. The rest of the universe will have vanished beyond the horizon, lost to us forever. Future astronomers may have no way of knowing that billions of other galaxies ever existed. We live in a special era when the cosmos reveals its vastness to us. Appreciate this fleeting window into the grand tapestry. Tonight, the universe is still visible in all its glory, and you rest beneath skies filled with the light of countless distant worlds. In the far future, the universe may become a vast, cold emptiness where even spacetime itself decays. Cosmologists speak of the heat death of the universe, a state of maximum entropy where no useful energy remains. Stars will have burned out, black holes will have evaporated through Hawking radiation, and matter itself may decay into scattered particles drifting endlessly through the void. Temperatures will approach absolute zero across the infinite expanses of empty space. Some theories even suggest that spacetime itself might eventually become unstable or undergo a phase transition into something utterly alien. This ultimate fate lies so far in the future as to be almost meaningless, trillions upon trillions of years away. But it reminds us that even the grand cosmos is impermanent. Right now, however, the universe is young and vibrant, filled with energy and potential. Rest well in this golden age of stars and light. Yet in this moment, spacetime is alive with light and matter, and the quiet presence of beings who wonder about its nature. For all the grand scales and abstract concepts, what matters most is this present moment. You are here, breathing, resting, contemplating the nature of existence. The universe is not just a collection of particles and fields, it is also the experience of those particles becoming aware. Spacetime holds galaxies and stars, but also thoughts and dreams. You are a part of this cosmic story, a temporary pattern in the fabric of reality that has learned to ask questions. The same forces that shape black holes and bend light also beat your heart and fire your neurons. You belong here. As you drift towards sleep, carry with you the quiet knowledge that you are woven into the very fabric of spacetime, held gently by the universe that gave you birth. Rest now and let the cosmos cradle you softly through the night. And so our journey through the fabric of spacetime draws softly to a close. This sleep documentary has carried us from the union of space and time into the warping caused by mass, from the event horizons of black holes to the ripples of gravitational waves crossing the cosmos. We have drifted through the paradoxes of time dilation and the mysteries of the quantum realm, where spacetime itself may emerge from something deeper. These gentle science facts to drift off to have traced the invisible architecture that holds all existence together. If this documentary for sleep has helped you rest, consider subscribing to continue your journey through sleepy science with us. There are more wonders waiting in the vastness of the cosmos, ready to carry you toward deep sleep whenever you return. Right now, as you lie here, spacetime curves gently beneath you, shaped by the earth below and the stars above. The same fabric that bends around black holes and ripples with gravitational waves is the quiet stage upon which your breathing rises and falls. You are not separate from these cosmic truths, but woven into them, a small warm presence within the vast tapestry of the universe. Let your eyes rest now if they have not already closed. Feel the weight of your body sinking into the surface beneath you, following the gentle curve of spacetime that holds you. Let your breath slow to match the patient rhythm of the cosmos, where billions of years pass like soft sighs. Release any remaining tension from your shoulders, your jaw, your hands, and let the fabric of the universe cradle you completely. Tonight, as you rest, spacetime continues its quiet work. Stars bend light around them in silent arcs. Gravitational waves from merging black holes pass through your body without a whisper. The universe expands moment by moment, carrying galaxies farther apart while you remain peacefully still. Time flows differently in every place, on every moving object, and yet here in your rest, it seems to pause, waiting for nothing but your ease. You are a small, warm presence within this infinite fabric, peacefully resting among the wonders. Sleep well, sweet dreams. And may you carry with you the quiet knowledge that you exist within something vast and beautiful, a universe where space and time are one, bending and flowing around every atom of your being. This has been Drowsy Discovery. Good night.